Okay, let's get started. I sent out an email about this, but I want to draw your attention to office hours. If you go in the course links over here to the left on Blackboard, there's office hours schedule. This is the weekly schedule, and it's basically all day Tuesday and Thursday. You have somewhere to go to get help. I'm at 9:30 to 11:30. Kirk is at 11:30 to 1. Jason's from 2 to 5 on Tuesdays, and then LP's from 2 to 5 on Thursdays. So you basically have 9:30 to 5 with an hour break there for help. And so what we'll do is most of the time we'll just collect have homework collected Wednesday and Friday. So that way for starting on Friday. Okay, so we may have some homework Monday sometimes, but most will go to a Wednesday, Friday homework schedule. That gives you the whole day of office hours before it's due, Tuesdays and Thursdays before it's due Wednesday and Friday. So I'll try to minimize the homework that's due on Monday. But sometimes we'll need to do that. But I'll try to make that a minimum. Okay?
Mark, the tutoring center opens Monday,
so tomorrow it won't be there.
No.
So this Wexler PSA 303 is the tutor. That's a tutor center for all math. But you want to find these guys because they know what, they're here in lecture with us. They know the approach that I'm taking to the course, which is slightly different. Okay, so you want to find these guys in that tutoring center when you go. Okay, look on the schedule. But that doesn't open till Monday. So in terms of tomorrow, if you want to get some support tomorrow, email you for appointment in your office. You can. I will be in my office tomorrow morning, normal. But those guys, just for tomorrow, you'll have to, for Kirk and LP, you'll have to, or Jason might be available, but you could email them and set up an appointment in their normal office. But then this PSA Wexler 303 begins next Tuesday, okay, for you guys. Questions on office hours? Okay. All right, so let's talk about the homework. So anyone have the hard textbook with them? No? No one brought it with them? Oh, thank you. Awesome. So I want to just look at maybe one of those that I would guess difficulty. Here we go. Okay, so did you have to do 25?
Yes.
How about that one? Okay, so here was 25 that you did for today. And so remember that the chain rule says if you have a function g of f of x, its derivative is what? You're going to do the derivative of the exterior function, keeping the interior as it is, and then the chain part, you're chaining on the derivative of the interior. And right now we're working on antiderivatives of this form. So antiderivatives are on the lookout for something of this form right here, and we want to collapse it back together, and we're trying to recover this original composite function. So we're going to start learning several different techniques for antiderivatives. This is always going to be the first one you look for. It's the most common one that shows up. So this, you'll always be on the lookout first for this undoing the chain rule. If it doesn't apply, then we try something else, because it's the most common one that shows up throughout the course. Okay, so what are we looking for? Essentially we're looking for two parts such that one of the parts is one of the parts here is the derivative of the interior of the other part. See that? One of the parts is the derivative of the interior of the other part. And if we have that pattern established, then we're going to undo the chain rule, and we're going to focus on this, because this is almost the same thing as what we're trying to get, right? If we're going backwards, we find this composite part, and all we're going to do is do the antiderivative of the exterior function, and that's basically it. We just have to figure out what factor we might need. It's a little mess to clean up. Okay? So this one, first of all, we've got a ratio. So how can a ratio be made to look like a product? So we've got x. So how can we make that x times something? Right. So if we identify what exponent 1 over the square root is, right? 1 over the square root is the same exponent as negative 1/2. So now it looks like it could have this form. So how do we know that it does? Again, the check is that we've got one term one of the factors is the derivative or something like the derivative of the interior of the other. So do we have that? Yeah. So x is essentially the derivative of 25 minus x squared, give or take a factor, right? Give or take a factor. We've got the right power. That's the important thing. X is power 1, x squared is power 2. So x is essentially the derivative of x squared, and we can take care of the factor that's missing. So this fits it. So which is our thing that I've circled in blue here? Is it Exhibit A or Exhibit B? Exhibit B. So Exhibit B here, this is like our composite function. And also the main gist of this is, to get the original function, we're just going to do the antiderivative of the exterior function, right? We have g prime f. We want g of f. We have g prime f. We want g of f. So we're just going to do the antiderivative of the exterior function. So we make a first attempt, right? So we say first attempt. Because in that first attempt, we might be off by some factor. We got to just figure out what factor we're off by, and then we'll be done. Okay, so the first attempt is to do the antiderivative of the exterior function. So what's the antiderivative of 25 minus x squared, or actually something to the minus 1/2? What's the antiderivative? So it's going to be leave that thing the same, and then to what power? Positive 1/2. But then we need a 2. So that's going to be our first attempt, right? We're basically looking at the exterior function, and we're saying, what's the antiderivative? Leaving the interior function as it is, right? I've got f here, so I'm going to keep it as f there. And then we're going to take the derivative and check it. But so we're learning antiderivatives based on our knowledge of derivatives, right? We're going to build off of what we know about derivatives in order to do antiderivatives, instead of learning something totally new and different. So we're going to take the derivative of this, and we're going to get 1/2 times 2, 25 minus x squared to the negative 1/2. All's good so far. But then by the chain rule, right, we're doing that derivative, so it's chain rule, times what? Negative 2x. Derivative of the inside is negative 2x. So we're going to compare this to what we have here, and we just got to clean up the mess here. So 1/2 times 2 goes away. And how is this different from this? We have an extra what? Negative 2. Which we don't want. So how do we adjust our first attempt so that when we take the derivative, the negative 2 won't be there? We need another factor of negative 1/2 on our first attempt, which will make 1 with a negative 2, and then our derivative would be exactly what we started with. So our second attempt then is going to be the same thing as before, but what factor do we need to eliminate the negative 2? We need a negative 1/2. So it would be negative 1/2 times the same as our first attempt. And then if we took the derivative, we would get exactly what we started with. Therefore, our antiderivative is correct. If we took the derivative of that, we would get exactly what we started with. And we can simplify this. Negative 2 times 1/2 is just negative 1, or negative 25 minus x squared to the 1/2. And then we're going to evaluate that from 0 to 3. And so in general, this integral expression here and this expression here are computing what kind of thing? What kind of thing? That integral expression is equal to this, which is something we can compute by hand now. They both equal what kind of thing? What kind of, yeah. They both equal a rate function. Agree with that? Nope. Where's the rate function? What's the rate function in this problem? Red for rate. This is our rate function, right? This is our rate function here. So this integral expression, which is the same as this computable expression, are what kind of thing? Amount of change in some quantity. They're the amount of change in some quantity whose rate is that red one. The amount of change in some quantity as x goes from 0 to 3 at the rate of that expression I've underlined in red. Okay, so this is then, so we're going to get a value. Right? It's the amount of change in a quantity. It's a value. You're going to plug 3 in, you're going to plug 0 in, and do the math right, and you're going to get a number. And that's what that original expression equals. And it equals a change in some value of some quantity as x changes from 0 to 3. Question?
And would it be plus c? Because it goes from 0 to 3, right?
Yeah. So, and if you could have plus c, right? So there's actually lots of antiderivatives. You know, any constant you could add. When you plug the 3 in, you'll have plus c. When you plug the 0 in, you'll have plus c, and then there'll be c minus c. They go away. Does that make sense? So you can have the plus c there or not, and you'll still get the same change in the quantity. Other questions on this example? Okay, so most of class we want to just practice more of this. So that the homework was a warm up. Let's practice more of these. Because like I said, this is the most common types of antiderivatives we're going to see. So let's just start by practicing the chain rule. Again, this is all based on our knowledge of the chain rule, really understanding the chain rule well, and taking that understanding to think how we would work backwards, okay? And that's the structure that I'm giving you, is working backwards. So let's just do some chain rule derivatives. Let's do those. So work on these derivatives, just so we're really in chain rule mode, okay? Chain rule mode. So these are, find the derivative, dy dx, or y prime, for these functions. Go. Derivative of tangent.
Secant squared x.
Secant squared. So in this case, secant squared what?
Sine x.
Okay, questions on those? So the whole point that we're making here is in terms of when we come to an integral and we need an antiderivative, we're on the lookout for something like this that follows this, the pattern that for all three of these. We're on the lookout for something that follows that pattern. Right? The pattern is, for all of them, is like this. We're on the lookout for a composite function with an interior function and then times the derivative of the interior function. That's what you did in these derivatives. And we want to recapture what? G of f. So we're going to focus on that and we're going to antiderivative G of f. Okay, questions on these derivatives? All right. So I think we did this one in class last time, so let's just do, here's just a bunch. Okay? So this is ones that we're on the lookout for, undoing the chain rule. Okay? So we're going to give you most of the time here. Maybe, what time is it now? 6. So let's go with 15 minutes. 15 minutes to work on these, work together, get help. But like I said, this type will be the most common that we see all semester, so we want to really have it under our belt, okay? Okay, so I put the answers to 1, 2, and 4 up there. I think those are the most straightforward ones. So you can check your answers and then keep working on 3, 5, and 6 for another about 4 minutes. Okay, last couple minutes. Okay, I'm going to do number 3. So for number 3, the first thing is we got to get it to be a product. So it's 2 to the t times what? 2 to the t plus 3 to the negative 1. So now it looks like it could possibly be our undoing the chain rule. And so are we going to focus on 2 to the t, or are we going to focus on 2 to the t plus 3 to the negative 1 to get the antiderivative? Second part, right? And now we need to do the antiderivative of something to the negative 1. That's basically the problem, right? Basically the problem is antiderivative of something to the negative 1. Something to the 0? If you do something to the 0, and then you do what happens? Then 1 over 0. 1 over 0 times something to the 0. So all these warning lights should be going off, right? You can't have 1 over 0. Something to the 0 is 1. All the variable goes away. So that's your warning that something's different about this one. It's not the power rule. So when you have an exponent negative 1, you're doing antiderivative. That's the one case that's not the power rule. What is it? So what has a derivative of something to the negative 1 or 1 over? That's natural log. So the antiderivative here is natural log. So you got to be on the lookout. And then we do antiderivative natural log. You need absolute value. That's another discussion for another time. Okay, so that's our first attempt. That's our first attempt. Okay, and now we do the derivative of that to check it. And then I showed you, I gave you up here, I don't know if you noticed, I gave you what the derivative of, say, a to the x is, in this case 2 to the t. So the derivative, our check, is going to be 1 over 2 to the t plus 3 times the derivative of the inside, interior, which is 2 to the t times ln of 2. So now, how is that derivative different than what we started with? We have an extra what? Factor of ln of 2 that we don't want. So, second attempt at the antiderivative. It's going to be, like I say, 1 over natural log of 2 times natural log of 2t plus 3 plus c. So again, when you have power rule, you're doing antiderivative of power rule. The one exception is if your power is negative 1. But even if you try to attempt the power rule, you should get the warning signs, right? You're going to get to the 0. And that makes the whole quantity equal to 1. And then you're going to have 1 over 0. You can't divide by 0. Unless you're Chuck Norris. You can divide by 0, but none of the rest of us can. Okay? So that's your warning signs that something's different about this one. And that's when you're applying natural log. Natural log has the derivative of to the negative 1. Okay, so let me just, a side note here. The point of this structure that I gave you, first attempt, derivative, second attempt, is just to give you something to get started with. But the goal is that you can kind of start to look at them and just write them down. You don't have to strictly follow the structure because you're seeing them as the result of chain rule. Okay, it's like what function has this as its derivative? What factor do I need to clean it up? Okay, so I don't want you to get locked into this structure. I just gave you the structure to kind of get started, but it's really about thinking of these as results of chain rule, and I just want to get the original function. So that's when it starts getting faster, and that's when the real advantage to this comes, when you start to just see them. Like, so these, I don't remember them. I just wrote them down. I wrote down the answers because I could do it in my head, and that's where you should strive to be too. I didn't have to go through the structure. I kind of did the structure in my head, but I was thinking of what functions have those as their derivatives, knowing that it's the result of a chain rule. Okay, so so don't. if you want to break free of the structure because you know you can do it faster, that's what I'm encouraging. Okay. All right. So should I do 5 or 6? Which one? 5 or 6? Probably 6. Okay. So I'm gonna. Can I erase everything I've written as solutions? Are we good? So some problems you're gonna do some algebra first. There was one in your homework, and it was something like this. Was it square root of x times square root of x plus something? Plus 1. Like this? Is it undoing the chain rule? If it's undoing the chain rule, then this is like the derivative of the interior. Is it? It's not. You see that? This is not the right power to be the derivative of the inside here. So what you do instead is you just distribute, and then you got an easy one. You just do power rule on each separately. It's not undoing the chain rule at all. So you have to be on the lookout for problems where you're going to do a little algebra first to your rate function, and then you have something easy or something that you can do. Okay? So that's how you did that one in the homework. So this is the same thing. Now we've got a fraction. So we want to start by rewriting this as sine over cosine plus secant over cosine. So change the form of the problem. You will get problems like that where you have to do some algebra first. Okay, so what is sine over cosine? Okay, that's tangent. What is secant over cosine? So cosine is 1 over secant. So if you simplify this, you get secant squared. So can we do either of those individually? Because it's a sum. So we kind of got two problems now. Antiderivative of tangent, antiderivative of secant squared. Either of those can we do? Should recognize that this is just a basic rule. It's a derivative of what? Tangent, okay? So if we're doing the antiderivative of secant squared, that's just from our memorization of all the trig rules. The antiderivative would be tangent. Now what about tangent? Is there one of the rules that you memorized that had a derivative tangent? No. Okay? So your basic trig rules, none of them, if you take the derivative of one of your basic trig functions, do you get tangent? So we need to do something else. And what we need to do is we need to go back to sine over cosine. Okay, so this one's we're done. Antiderivative is tangent. But this one, we go back to sine over cosine, and what do we have? We have sine x times cosine x to the -1. Does it fit undoing the chain rule? We have a composite function here. Is this essentially the derivative of that offset by some factor? Yeah. You see that's kind of like our f prime. And this is like our g prime f. So we're going to focus on this one and do the antiderivative of the exterior function. Antiderivative of cosine to the -1 would be? She's got it. What about the rest of you? Antiderivative of cosine to the -1. It's going to be natural log again, right? So we're going to have the natural log of cosine x. That's for this one. And then plus antiderivative of secant squared. It's tangent x. But then we do need to check, right? We need to do our check. When you do the derivative of this, do we get this? No. How is it off? What is it off by? Factor of -1, right? We do 1 over cosine times negative sine. We don't have negative sine. We just have straight up sine. So our adjustment is negative natural log of cosine x plus tangent x plus c. Okay, just quickly as you're quietly packing up. So the homework for Friday, it'll be our first homework on what's called web work. It's an online online homework that's free to you. All the details will be on Blackboard. It will be practice of this stuff, the first web work assignment. We'll see you Friday. There will also be a written portion on Blackboard. There will also be a written portion.